Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to provide an example of how to apply Lenz's law. So first let me talk a little bit about where you apply Lenz's law. So anytime you see a changing magnetic flux, that will mean that you've got a potential difference coming, right? So anytime we change magnetic flux, we're going to get a potential difference, or sometimes called an induced EMF, and the induced EMF is equal in magnitude to the rate at which the flux changes. So that might look something like a changing magnetic flux over change in time, or in the language of calculus, the time derivative of the magnetic flux, again, where the magnetic flux is BA cosine theta. I'm just going to focus on this video, the polarity of the induced voltage. So what we're looking at here, we've got this magnet here, and I've already took the liberty to kind of sketch out what the magnetic field lines might look like around that magnet. And in this example, we're going to assume that that magnet starts moving towards this region over here. Now, the region I'm referring to here, we've got an iron core with a wire wrapped around it, and the wire's got this resistor in it. And what I'm going to do is try to apply Lenz's law to figure out the current direction in this resistor, right or left. So again, we're going to be talking about when the magnet is moving towards the iron core. So as this magnet moves in this direction. Now, notice some things here. Notice that right now, basically all the field lines that I have drawn are going through this region, whereas before they didn't. So what that's telling us is the magnetic flux over on the right is increasing. See how the number of field lines going through this vertical cross section is getting larger and larger and larger. All right. The other thing you need to consider is what the magnetic field direction over on the right looks like. Now, remember that these field lines point towards the south magnetic pole. So for example, this point in space right here, the field line points this way. Here it points this way, and so forth. So in this configuration, with this magnet here, the magnetic fields over in this region point this way. That's because these field vectors are basically pointing right to left. And again, as the magnet gets closer, as it moves to the right, like so, these magnetic fields would be getting stronger. Lenz's law is nature hates a magnetic flux. As the magnetic field vectors get stronger and stronger and stronger, that's going to induce a current in these windings that will set up its own magnetic field to oppose the change in flux. Since these vectors would be getting stronger, the induced magnetic field would go in this direction to oppose the change in flux. If these fields were getting weaker, that would be occurring if this magnet moved to the left, then the induced magnetic fields would be trying to support these to oppose the change in flux. So again, with the magnet moving to the right, these magnetic field vectors are getting stronger, so the induced field would be this way. Now just mentally grab the wire somewhere, picture like this spot right here, and ask yourself, what would the current direction be, this way or this way, to give me a magnetic field in this direction? So you apply right-hand rule, just mentally, if you're watching this video, mentally grab that wire, thumb in the direction of the current. Your finger needs to roll around in the magnetic field direction. Now if you grab the wire with your thumb going this way, the field vectors would point to the left. And that's not what we want. We want them pointing to the right. You have to grab the wire with your thumb in this direction so that the induced magnetic field is this way. And then if you just kind of follow that current around, current's going to be in that direction in the wire. So just meant this to be a very short video here on on applying Lenz's law. I think what I'll do is just pause the video, set up one more. It's short enough. I think I can get a second example in this video. So if you just stand by. Okay, I'm back. I got another example here. We have a wire here with a current to the left as shown. We have some sort of current loop, which I mean to be kind of like, if I put a coordinate system here like X, Y, Z, imagine this current loop is in the XY plane right below this wire. And we're going to imagine that this current is dropping. And then we're going to talk about, how does that affect the wire loop here? So the first thing you need to realize are what the magnetic field lines around this current look like. Field lines around a wire are circular. Oops, I can draw better circles than that, I think. Let's try this again. So they're looking something like this. You tell which way by right hand rule. So you just kind of mentally grab the wire, thumb in the direction of this current, and what you'll find is that the field vectors point like this. So if we are down here, below this wire, the magnetic field vectors would point in the plus K direction. And that's the magnetic field due to that current. Now, if the current is dropping, then the magnetic field strength in this region is dropping, which means the magnetic flux through this area is dropping. That means we're going to get a voltage and a current over here. Lenz's law will tell us the polarity of the current. So these magnetic field vectors are in the plus K direction. They are based on this current, and that current is decreasing. Therefore, these magnetic fields are getting weaker. Therefore, the induced magnetic fields would be in the same direction to oppose the change in flux. Then just pick a spot in the wire, like maybe right here, and ask yourself, which way do I have to grab that wire with my thumb going this way or this way so that the magnetic field points plus K direction in the interior? And the answer to that is in this direction by right hand rule. So in this example, with a current to the left decreasing in strength, that's going to induce a counterclockwise current in my loop over here. So again, I hope that these examples help demonstrate how to apply Lenz's law. Have a great day.